After having laid the foundations for routing, explaining the basic concepts and algorithms, let's focus on concrete examples of routing protocols in the internet, OSPF, BGP, and some others. So first of all, what is the topology? We had this already in the starting chapters. The topology of the internet, well, the internet consists of many so-called autonomous systems. A large number, several thousands of them, autonomous systems. They belong to organizations. Organizations can have several autonomous systems, and the organizations determine what happens inside the autonomous system. So there are, as shown here, several routers inside of an AS. All the ASs are operated independently. Now, what is important, all the ASs are connected to the outside world, and this is exactly where the ASs have to follow certain common protocols. So all those routers acting as a gateway to the outside world, connecting with other ASs, they have to use a common exterior gateway protocol. We'll see examples for this. Internally, inside an AS, you can use more or less whatever you like. You use the interior gateway routing protocol, IGP. And there could be different interior gateway routing protocols depending on the AS. Or you can perform flooding if you like, or static routing, or whatever you like internally, as long as you follow the common exterior gateway protocol that connects all the ASs. Okay, so now let's have a look at one of the first examples, a classical one, a historical one. The Routing Information Protocol, specified in RFC 1058, so it's a bit older. And that was the first interior gateway protocol used in the internet. And that's exactly one of the representatives of this distance vector routing. Packet-oriented, flat, proactive. So by now you know what this means. I explained all the differences. And the idea here is that for distance vector protocol, you have to exchange neighbor information. This is in RIB. This is done every 30 seconds as a UDP datagram. And the metrics is very simple, is the number of hops. Remember, we have the count to infinity problem, and this is why we limit the maximum number of hops to 16. 16 is infinite, so we limit it to 15 because 16 is already infinite. Okay, so, and we have certain other parameters like maximum number of entries in a message, etc. So this fits for small systems, not too many routers. You see, small number of entries and the maximum number of hops limit to 15. There are some advancements like support of subnets, of CIDR, some authentication, but still we have this hop limit. Also IP version 6 extension. So that was the starting point, but not so many networks use it anymore. You can, so there's RIB support, but the protocol typically used today for interior gateway protocol is called OSPF. OSPF, Open Shortest Path First. That's a bit newer, and there are versions for IP version 4 and IP version 6. So actually now the new version is address agnostic, so we can support 4 and 6. Now this is a link state protocol supporting hierarchical routing, also packet-oriented proactive. We talked about this. Now what is the big advantage? Well, we support different metrics, not only hop, but also something like delay, for example. So it can adapt fast to changing conditions, supports load balancing, which is quite interesting, hierarchies. We have a certain protection for routers for wrong routing information or attacks. So that is a bit more modern protocol. Okay, so today OSPF RIB, that's the older one. So hierarchies, what does it mean? Well, OSPF supports different types of routers. So there's one type, internal routers. Internal routers, they belong only to one area. For example, the dark blue one, the light blue one, the green one, the brown one. They belong to one area. It could be, for example, a backbone. Then we have area border routers, and those area border routers, they connect two or more areas. So, for example, this router here, and router here. So they connect different areas. So they form then part of the backbone. The backbone itself is also area 0. And the routers inside the backbone are then also called backbone routers. Backbone routers, so they are also internal to the backbone. But here all these blue ones are then backbone routers connecting different other areas. And then we have a fourth group. These are our border routers to other autonomous systems. So, for example, here this blue one now is a border router, and this border router has to speak an exterior gateway protocol, but also an interior one. So this AS border router speaks two protocols, IGP and EGP. And the idea now, and this is why this is hierarchical, within an area, all the routers have the same link state database. So you remember, for these link state algorithms, we create a database that reflects the current topology. And in this case, the topology of a certain region. And if you're one of the light blue routers, well, you have the same database as all the other light blue routers. But the routers connecting two areas, they need link state databases from both areas. So, for example, if you're here routers, those two routers connecting the areas, then it depends on the configuration. For example, the dark blue one has to know something from the blue and has to know from the dark blue and from the light blue region. So that's the idea, that you say, okay, we have certain areas, we can introduce hierarchies to create larger, well, scalability. One of these areas, you shouldn't have too many routers in it, because remember, we always exchange the complete topology. So OSPF, that's typically used for many interior gateway protocols. Okay, there are some other protocols like AS that were standardized by OSI. So the IETF didn't really like this. AS or sometimes said, okay, this basically semi-zero doesn't work. It's similar to OSPF, so it's all based on link state, hierarchical, it's proactive, so that's pretty similar. But a big advantage from AS is it's neutral to the layer 3 protocol. And this is why that was quite interesting. So IP version 6 got faster support by AS compared to OSPF, because AS from the very beginning supports all layer 3 protocol. And OSPF was geared towards IP version 4. So it's pretty similar. Routers also build a map of the network. You calculate shortest path, and can be shown that the overhead of AS is somewhat lower compared to OSPF. And AS is quite often used by network operators with larger networks in terms of number of routers. So it scales a bit better compared to OSPF. So RIB, OSPF, AS. So routing internally inside a domain. And these are the pointers if you're interested in more details. A bit more interesting for us, now we have this intra-domain routing, bit more interesting is, okay, what happens now between domains. Within the network, you would all agree, we have a limit number of routers, then we can create this topology. This is one organization. Okay, fine. So, check. Inter-domain routing. Well, this has to find the path between networks. That can be more complicated because this is where money comes into play, also politics and companies with different interests, etc., etc., etc. Way more complex. Routing between the domain. But this is what we need to create the internet, consisting of many networks. So as we know, the internet is a network of networks. And the autonomous system is then one domain, for example, from Google, AT&T, the Telekom, the German Research Network, etc. They all have their autonomous system. They organize it internally however they like. And they all have an ID. So each autonomous system has a certain ID to identify this autonomous system. And then we as the end users, we somehow as a German universities typically belong to the German Research Network. We get certain IP prefixes, certain blocks, and then we can use our computers then get the IP address within these blocks. So that is basically the idea here. So now the big question is, how do you organize the routing between those autonomous systems? Because as I said, money is quite important. So why should AT&T forward traffic from the German Research Network? Why should Google do it? What is the motivation? So why should the traffic go across another network to someone else? Inside the network, it's one company, it's one organization. There is a clear motivation to keep the company running. But between the networks, why? Okay, many challenges. So the objective is, well, somehow we have to do this routing. So we have to exchange routing information between the autonomous systems. Okay, nothing new. That's the same we do also inside the domain. The challenges are now scalability. We have far more than 600,000 prefixes in these routers in the internet. We have, well, about 100,000 ASs, more than 1 million routers. Okay, that's quite a lot. Additionally, the networks don't want to really be transparent when it comes to internal topologies, also to their policies. So this is rather a black box. Yes, we have the routers at the edges, but the companies, they don't want you to see how they do something internally. And then there are many different policies. So money, political decisions, companies, etc., etc., etc. This makes it really way more complicated. But don't we have a solution? We learned, well, basically something about link state routing. We learned about distance vector routing. So let's pick one of them and see if this works. The problem is they won't. So why? What could be reasons? Well, why can't this work? Think of link state, for example. What does it mean? There was one thing in link state routing. Remember, flooding. Flooding worldwide networks, that's a problem. So for link state, flooding is a real problem. Also the processing overhead. When you have many components, think of, we have millions of routers. Okay, we limit this all only to the autonomous system, but still more than 100,000 autonomous systems. That's a problem. Then also, what is the distance? Do we have a common view on distance? Not really. So what about distance vector? Okay, distance vector, we don't see details of network, that's good, but the convergence is really a big issue. And also, what is this distance? Is it just hop count? No, we have money, we have policies, we have this and that. So the problem is we cannot simply say, okay, let's pick hop count, or let's pick data rate or delay, and then calculate the metrics. It's much more complicated. And it's also different between different networks and different policies. So internet routing is much more diverse. So we need support for a bit more than just link state, or this is the topology and this is the distance or weight of a link, a bit more complicated. And this is the reason why we need another protocol, BGP. And BGP is now the protocol for as an exterior gateway protocol to connect different autonomous systems. Okay, what is it? So in a nutshell, BGP is a path vector protocol. Okay, so it's not distance vector, it's not link state, but path vector. I will explain this. So the idea here is, yes, the routers, they talk to their neighbors. That sounds like distance vector. They exchange also vectors, so information about something, but now information about paths. This is why it's called path vector. Not just a distance, for example, a hop count, but paths. So the routers exchange path vectors with their BGP neighbors. They're called the peers. So those neighbors typically are connected directly. So there's a layer 2, a point-to-point connection. We learned about PPP in those protocols directly between one router, border router of one autonomous system with a border router of another autonomous system. So you have here your autonomous system, and you have here your autonomous system, and you have here direct connection. Maybe there's a switch in between layer 2, but that's it. So that's the idea. Okay, I will come back to peering, what you can do there, but typically the neighbors are connected directly via a switch. So there's also there are some other ways. Okay, now we exchange paths, and now we can have a look into the paths, and we can accept or discard the paths based on policies. So if I remember the example where we routed traffic across a country we don't like, however, if I detect a path that goes through an autonomous system from a competitor, although this might be the shortest path, I will drop it. And that's the difference, for example, to an OSPF based on link state. We do not automatically pick the shortest path, for example. It's not the classical Dijkstra. So we exchange paths. So we have certain policies. Could be the shortest path, could be also preferred neighbors. It could be whatever's available, sometimes called hot potato. So there are policies. And also the outgoing advertisements, what you advertise is also based on policies. So you will not always tell all your neighbors the truth about the internet. You should not lie, that's not the point. But you don't tell everything. So maybe you know that you can reach a certain autonomous system via this and that path, but you don't want to announce this to others. I will show some examples for this. But remember, BGP is really the glue of the internet. Without BGP, the internet breaks apart in many thousands of islands. Okay, so this is exactly if you connect Google with AT&T. Well, in the simplest case, you have a direct layer 2 connection between two routers, one belonging to Google, one belonging to AT&T. We'll come back to these scenarios, and then you can peer them, you can bring them together. So that's the idea. So how does it work? It's relatively simple. The policies are not. Altogether, it's not simple. BGP itself is, well, that's okay. So what the BGP peers, so the routers do, you establish a TCP connection, okay, between the routers. And that means, okay, I reach my neighbor, and the TCP connection is then used to exchange the information. And via this TCP connection, you exchange certain reachability information. Reachability, that means which prefixes do I see? Remember, this could be many. But I see these and that prefixes, for example. So that's reachability information. What do I see? And the list of AS numbers to reach a prefix. And this is my path. So that means I reach a certain prefix, 2943 for example. I reach this via certain autonomous systems. I reach this via AS 17 and 48. Then I can decide, oh, I don't like 48. So no, I will not use this path. Because maybe someone else tells me, oh, I reached the same prefix via 43, 49, 51. So I can make a choice. So maybe because I don't like 48, I don't use this path. So the router collects potentially redundant paths and stores the data in the routing information base. Then to select one of the paths, and then you can apply policies if you like or not. You simply take the shortest one or random or whatever. There are certain message types involved in BGP, so you can open, establish the peering, so you can update, announce, withdraw prefixes. You can check if your peers are still alive, and there's some error handling. Okay, so there is no periodic automatic route maintenance, so routes will be deleted when you withdraw certain received updates. So that's the idea. So there's no automatic permanent check that routes do exist, etc. Okay, so example, how does it work? We have the following setting. That we have these 4 autonomous systems, Google, AT&T, German Telecom, and the German Research Network. You see, well, or better, you don't see the internal systems, so there might be many routers internally. You only see the border routers. There could be several redundant paths, as shown here, between Google and AT&T. There are different ways between the DFN, German Research Network, to reach AT&T, for example. This can go either directly or via Google, or we could even imagine that maybe T-Mobile forwards traffic or the German Research Network to AT&T. Many things are possible, and you see there's also a network connected to the research network. This could be the university network, for example. So what happens now if we announce prefixes? For example, the German Research Network will announce, here this example, this direction, will announce, look, this prefix, 160.45/16, so this is our prefix here. You can reach this via me. In this case, okay, AS 680. And you see, this is exactly the prefix we have down here. Could be /16 network of a university, for example. You announce this to everyone, also to Google. This AS of Google receives this and then announces, oh, look, towards AT&T in this example, I can reach this prefix, 160.45/16, via me, and then 680 German Research Network. So basically each AS appends its own number ID when propagating the announcement. This is the path. This is why it's called a path vector protocol. And then in this case, AT&T could now decide if I have to send a packet to this network 160.45/16 to one of the computers here, I can go directly to via the AS 680, or I could also go via the AS 1569 Google and then to 680 in case, for example, this line breaks. So that's the idea, that all the routers will get a path, a list of autonomous systems a packet will travel through when forwarded to a computer that belongs to a certain prefix. So that's the idea. But you can imagine that this database is not that small, because there are many, well, prefixes that are announced, and there could be several paths. And if you receive such a information, then, just an example, you create a certain entry in your routing information base with a timestamp. I received this here and there. Then you get certain prefixes from where you got this. You see here also IPv6 addresses, and you store paths, and there's also certain metrics that can be stored, routing policy groups describing how to propagate routes. But besides these additional parameters, for us important is to see, okay, there's a certain prefix, that's the important part. How can I reach it? I store the path, and this is, I got the newest information from the AS 1569. So I got some information, I've got a path, and this is the way how you then, in the end, create this whole table, this routing information base, where this is the main, the important information that you know how to reach these different prefixes, and then there are many other parameters in there. So you create this huge information base, and then you have to select a path, because in the end what we want to have is a forwarding information base. So we have to make a forwarding decision. Okay, so you have typically you have many redundant routes to a destination. And so the first step is, what is your preference? So many local policies, attributes, and then you actually assign the preferences to all the entries. So this could be maybe certain contracts with network providers, or countries you don't like, or companies you like, or partners, or whatever. So money, etc., etc. So you assign the preferences to all the entries. Then you select the route. So for all these IP prefixes, you select one best route. So highest preference, shortest paths, etc. So many rules can be applied. So that is the idea. So then you say, okay, this is the best route to take to a certain prefix. And this is then also the basis for creating my forwarding information base. So what do I then actually use for the fast forwarding? But this is also the basis for the dissemination, because you then pick the path and disseminate this again to the neighbors if you want, depending on local policies, because maybe you will not announce everything you have in your database. So many, for example, will not forward traffic for other autonomous systems. Maybe sometimes they do, but they don't prefer to do this. So there are many different rules that say, okay, maybe only non-commercial traffic. So for example, the university networks will typically not forward traffic for commercial network providers. Okay. So this is what you have to do, and you see this is a bit more than the pure decision based on hop count, for example, or like a distance vector. So this is why this is called as distant path. There's always the path included in the decision. So how does it look like? Well, BGP is complex, and if BGP doesn't work, the internet doesn't work. So we have to be able somehow to look into the routing situation. So can we look into the routing tables? Yes, I mean, if someone allows this, so at least the ISPs can look into their own routing tables, and that's quite important for debugging, because sometimes the traffic maybe is a bit slow or the delay is high, and what is the reason? Maybe it's not an optimal path, and because it's a highly distributed system with many different organizations, the problem might be somewhere on this planet, and it's not really your problem, your own problem, but maybe the path you're using goes across an autonomous system that has a problem. So, an example, Sprint, a large ISP in the US, how do you reach a certain URL? Okay, we can look up this IP address for a web server, knowing, okay, this belongs to a certain block, and this block then originates by a certain autonomous system, 12306, German service provider. So then we know, okay, this publisher, Heise, got a certain address from an ISP, and the ISP is responsible for a certain autonomous system. And then we can look, okay, how do we now reach? If we are Sprint, how do we reach this web server? So that's the idea. Because maybe the customers of Sprint discovered, oh, there's a problem, and then Sprint wants to see, okay, maybe where is the problem? Then we can look into the router. So Sprint can look into the router and can check, okay, this is now for this web page. Okay, this is the prefix we use. Okay, and how do we reach then quite concrete this prefix? And then there might be different entries telling you, okay, there are certain paths that can be used, and there are several available paths that can be used, and this router received the paths from different other systems. Okay, and the ASs, by the way, just noted some of them because, well, you have to look it up where those ASs belong to. So AS 3356 here is level 3, 2914 NTT, 3320 German Telecom, etc. So this has to be looked up. So, but if we check, for example, now a Sprint router, also Sprint, in Frankfurt and not in Chicago, okay, we see completely different information. You see here that suddenly, okay, we go, in this example, via NTT America to the provider of the web server of Heise in this example. Or we can also go via Deutsche Telekom to this provider. And you see the information is derived from different systems, different metrics, etc. And we have here different available paths, and we can pick one. But what we also see is, well, even within the same company, here in this example Sprint, it depends on the router where we look at. It depends on the vantage point where we look into the network. So you cannot say for this organization it's always this and that path. So it really depends where you look into the network. So that was just an example. So how to reach, in the end, this is always the company that gave the IP address to, in this case, heise.de, how we can reach it. Very short paths, as you see, so we do not go through many autonomous systems, here just 2 of them to reach the router. But what is quite important, really the routes, they depend on the vantage point. So it depends, and This is also why you cannot say, okay, this is the internet composed of all the available routes, because it depends on, well, your vantage point, where you look into the internet. Depending on this point, the routes look different, and then the internet looks different. Okay, so this makes it a bit more complicated also when we talk about problems in the internet, problems arising. Then you cannot say, oh, this is the topology. Yes, I mean, a single router then has a certain partial topology of the internet. In the ideal case, all the routers can reach all the end systems with a globally unique IP address, but they all have a different set of paths to reach the end systems. So, what are the players and how do they interact? Well, we have the AS operators, and the operators, they are responsible that their set of IP addresses can be reached. So, the IP addresses of their customers and their IP address, so their prefix should be reached. And not only that they can be reached, but maybe there's also an efficient way to reach the customers. And you can imagine that, okay, if you now have autonomous systems like this, these are all our autonomous systems. And yes, they're interconnected. And even with this setting, the internet works. And if we have here a customer with a host and this AS1, and we have a customer with a host and this AS7, for example, then this host goes via several routers to this one and could then forward the traffic. Maybe here again some routers. Here the traffic forwarded here. Okay, but why should those two networks forward the traffic? That's a good question. Well, the interest here is quite clear because the operator of autonomous system 1 wants to offer the customer a good internet service. So yes, I will forward your traffic because maybe you pay for your IP address and this and that. And also here, the operator of AS7 also wants to assure that the customers receive all the data because, yes, you paid me. But why those two ASs in between? Why should they forward the traffic? And by the way, this is also not optimal. I mean, maybe if there's just a little bit of traffic between AS1 and AS7, then that's okay for those ASs in between. But if there's a lot, then maybe they don't like this idea of forwarding. And also the customers may experience delay. So maybe it's a good idea to have a direct connection between AS1 and AS7 to start peering, to bring those two ASs close together. And the idea in the end of all this peering is business. I mean, you have certain providers that have their customers. The customers, they pay money to get connectivity. But, well, if you just do this peering without the customers, you just together, like in our example, the ASs where they just forward the traffic, okay, is there money involved? If you just come together and you don't have directly the end customers, well, here, the point is peers typically don't pay. They exchange the prefixes of themselves and of all the customers, but why do they do this? Because they say, okay, it's for the benefit of both of us. So we will have customers sending data to you, you have customers sending data to us. So it's a good idea if we directly come together, if we directly do this peering in our example, maybe directly AS1 and AS7, because our customers want to exchange data, we want to have a low delay, a good quality of service, and so on. So, but how can we involve money in all of this? So, and how is all this, well, who pays? Typically for the pure peering, in this the lower example, we don't pay. So we just think it's quite balanced. But for real customers, well, there's the customers in the end, they have to pay because the customers, like the German Research Network, they want to have connectivity, in this example, very simple examples, via German Telecom. And then one idea is that you say, okay, we check every 5 minutes and check how many bytes do we receive and how many bytes do we send. Quite concrete. What does it mean here, 95th percentile rule? Well, you get all these values every 5 minutes, whatever, of how many bytes send and receive, always send and receive, and have a long list at the end of the month. First step, you check what are the top values. So there might be some bursts. So you have a long list, and you have the top 5%. And that's bursts. They may happen for downloads and whatever. And you simply ignore them. And you base the billing on these normal 95%. So how many bytes did I transfer for you? That's the idea. So we can discuss if this makes sense. This is more or less accepted. That you say, okay, we ignore the bursts and we make the paying based on the 95% of the remaining values. How much do you get? Well, less and less per bytes. So if German Telecom, for example, transfers data for us, so because we will access whatever network somewhere, then yes, you charge for it, but fewer and fewer. So 98, it was still quite a lot. You see here transit prices in the internet per megabit per second, and this goes down, and you see it dropped here in this example, dropped every year. So it's not that much. What is the reason for this? Well, because much more competition, many more companies, and the internet is just everywhere. It's nothing special anymore. So we're talking about gigabits, and you access everything from everywhere, and no one thinks of, well, the cost per bit. It's just there, which is a problem because if you really install infrastructure, that is quite expensive, and you will not make that much money out of infrastructure. So this is really one of the problems. We see the same effect in wireless communication compared to the cost of cellular minutes. Well, we don't have minutes anymore. Cellular bytes just 20 years ago compared to now, where you have flat rates and megabits and up to gigabits per second. So the same trend. Okay, but coming back to BGP. BGP, we have many policies. And you saw that, yes, we get all the paths and we collect the paths in the routing information base. But it's a question of, well, which paths in the end do we select for ourselves? And which paths do we advertise to all the other routers, to our neighbors? So the selection in the end controls the outbound traffic. So I decide which path, if I have several paths for a certain prefix, I decide with which path to use, and this controls my outbound traffic. So which path do I take to a certain destination? An example for this. Assume the following setting. We have here collection of certain autonomous systems, those little clouds, and they all have connections they have to pay for. So the university, in this case, pays money for using the German Research Network, or better, we pay euros. and so on and so on. And then there are some agreements, peering agreements, here for example between the Deutsche Forschungsnetz, DFN, and a company, etc. Why? Because we don't want to go the way across German Telecom paying something for it. So if you want to avoid this, you can create the peerings, and then we don't have to go this way. So that's the idea. Okay, that's the setting. And now the question is, which routes do I prefer? And there are certain rules. Let's say, okay, we first, for a certain prefix, we prefer routes from customers. Customers pay money, because so I get money from the customers. So if I get a certain path, a route from a customer, I prefer this over path that I got from peers. With peers, I don't get money, I don't pay money. Okay? And then the last one to take, if there are no routes available from customers or peers, I go via providers, because then I have to pay. So it's for a certain destination, I prefer customer, because this is where I get some money, and there's basically nothing for the peers, and for the providers I pay something. So this is a simple rule for selecting a certain path. So which path to use for the outgoing traffic. But which one do I export? So which path to advertise? And this controls inbound traffic. Why? Well, if I advertise to someone else, hey, I reached this prefix via this path, it will happen that this neighbor then sends me traffic to this destination. I have to forward then. So exporting paths controls inbound traffic. So the question is, again, for the same example, which routes do I export to whom? So, would you, for example, say, okay, exporting certain paths or inbound traffic, should this always go, in our example, across German Telecom or not? Or do I export certain shortcuts? And there's also there are some rules for this, that providers, they transit traffic for their customers. That, in this example, the German Research Network will transit the traffic for the customers. We as a university, here we are a customer. So our traffic is transited to, in this case, into the network of the German Telecom. And if we talk to our local government, then we have here this peering. The traffic goes here, for example, to this system. So this is what our provider does for us, because we pay our provider. But what peers typically do not do is they will not transit just, well, between each other. So there's no reason that you simply here, as this company in between, that you transit the traffic here across here to someone else. So because, I mean, there's no money in the end, there's no money involved, and why should you do this? I mean, you just transit the traffic. So peers don't transit between each other, so this is typically not done. And also, what is not done, customers do not transit between providers. So there's no way that traffic flows here from one network across the customer to someone else. We don't even, as a university, we don't even if we have this direct connection to other networks, which we do have, we will not then forward traffic. So this is something we don't do. So there's, not even this type of forwarding. So this is not done. So the customers, they don't transit between different providers. So that's not our job. So typically follow the money, then you know where the traffic flows. Very simple rule, just follow the money. Okay, so so let's assume we have just an example provider here. We have our customer and we have a peer, just in the previous example. Then we know that the customer pays. We have peers, so this is where the money flows. And this means, for example, the provider, if the provider gets a prefix from a customer, the customer has a certain prefix here, then the provider will announce this prefix definitely to other customers of the provider, will announce it also to other peers and also to other providers. Well, because it's in the interest of a provider to make the customers happy, this is why we announce it to everyone. That, hi, I am the provider for this customer and this is the prefix, so everyone knows. But if I get a prefix from a peer, that the peer tells me, hey, look, these are prefixes, then I tell this only to my customer because I got money from my customer and I want to have a situation where the customer can really reach everything in an efficient way. And this is why I will then announce this prefix to my customer, but not to other peers or other providers. Because say, it's their problem. Because I will not transit the traffic on behalf of other providers across my autonomous system. Then the same is true for if I get a prefix from another provider. Yes, I will tell my customer, that's important, but I will not tell other peers or other providers, because those peers should have their own peering if they want. So that's the basic idea. So rule of thumb, follow the money. Very simple. If I don't get money for something, I don't offer a special service for it. Very simple. Okay, now we saw some examples with some ASs, but how do we then organize the internet? Are there different types of ASs? And quite often you can see a figure that looks similar to this, that we have a certain hierarchy with tier 1, the global internet cores, and run by some companies. We have some national ISPs, tier 2, tier 3 stub networks, and then you have the customer IP networks without, and this is not an AS, so they have no number. And there were also different business relations. So typically as a customer, you pay for the access. Well, for example, you have a 50 megabit connection, you pay for this, for the access. The tier 3s, they pay for the upstream, so you pay for the bytes, the amount of bytes, for example. And then it was the idea that you pay for bandwidth. And then there are different business relations between then the key player on tier 1. That was the classical way of looking at the internet, but this is not really true anymore. So it rather looks like this a model with many more interconnections. So we have the global internet core is run by huge content providers. So and those hyper giants, they really manage the content. So Facebook, for example, or Amazon or Microsoft, they have content, they manage consumers, they have cloud, They have also content delivery networks. There are many more companies. Plus, so companies mainly with what is important here, they also have content. Plus, you have huge transit and backbones. And they run the core. And then somewhere in between the core and the regional, well, also called tier 2 providers, you have IXPs. So you have companies, organizations connecting the different networks, the different autonomous systems of different organizations. Huge exchanges that bring together many different companies exchanging terabits per second and connecting this global internet core with the more regional providers. Providers, they operate in a geographic region or a specialized internet service provider. And in the service provider, you have then the customer networks, but they may also have direct connections to one of these backbones to get better performance for certain things. So it's many more interconnections between many different players here. And here you can see a link to one of the publications discussing this. So in the end, yes, it's always follow the money, but it's now way more complex because we do a lot more, especially those, well, giants. They're interested in not only hosting content, but also running worldwide networks. And the majority of the new installed global fiber networks are run by content providers like Facebook and Amazon and Microsoft and so on. So because then they can control the infrastructure, the content and everything together for good or bad. So you see, BGP is not simply an algorithm or only a protocol. Yes, it's routing, well, a system, a real complete system that takes care of the inter-domain routing, which is really different from intra-domain routing. With many different players, we exchange the paths for certain prefixes. We select one of them. And this routing information really depends also on the peering relations. And if you discover that you have a lot of traffic with a certain other network, then maybe start peering directly with these other networks. So also you saw that different BGP routers of a single autonomous system, we had the example of Sprint, may have different paths for the same IP prefix. So it depends on your vantage point, where you look into the internet, how it looks like. And the routing might be asymmetric. So it's not guaranteed that if you take from A to B a certain path, that you take the same path the way back. Not at all. So in the end, one of the pioneers in the internet said, well, there is no real synchronized overview. So you cannot take a snapshot that this is the topology of the complete connected internet. We don't know. So all the viewing points, that's the important message, contains always a filtered view of the network, filtered by many, many policies. And the point is in the internet, just because I cannot see certain paths, even certain parts of the network, does not mean that it doesn't exist. It could be somewhere, but from my vantage point, I simply don't see it. And just to emphasize once more, the scalability issue, just an example of the entries of a certain autonomous system, 65,000 active BGP entries, and you see it's more than 700,000 entries, which is quite a lot. That has to be managed by those routers. Okay, so, and if you understand a bit more about BGP, you way better understand this. Mid-January 2021, the government of Uganda decided to shut down the internet. What does it mean? Well, you simply do not announce certain prefixes And so there were 36 ASNs, so ASN numbers. They were in the beginning were visible, and this dropped down to 24. And if it's some AS is not visible anymore, then what is the result? 3 out of 565 IP version 4 prefixes simply vanished from the routing data. Okay, along with 9 of the 17 IP version 6 prefixes registered in the country. And you see here a dramatic drop in the visible IP version 4 prefixes. Okay, we discussed this, we saw this already with playing with DNS to stop people using the internet, and this is now on layer 3, one way of, well, actually shutting down the internet, making it impossible to communicate. And as people write here, no less than 44 million people are negatively affected by this. So the ISPs were really instructed to terminate service at the edge, so you don't announce anything anymore, you cannot send, receive anything. So by taking away the announcement of the prefixes, if I don't announce it anymore, well, the machines are still there, but unreachable, because no one knows how to reach the network. So yes, also BGP can be used for political issues, similar like DNS and other systems in the internet. Okay, but also besides this, we have many issues, challenges, problems with BGP stability, the growth of the routing tables. You saw more than 700,000 entries, load balancing, hijacking of routes, etc. And there are several pointers here where you can have a deeper look into this, what happens and how fast do paths converge. For example, if there is a change in the internet, how long does it take before this really propagates? And you see BGP is nothing for an immediate switch from one path to another. That was one of the motivations of MPLS. I mentioned this briefly, but so it takes some time before paths converge. There's also quite good analysis of what happens with certain attacks and what are the effects of even small autonomous systems on the global traffic. That, for example, 2 small ASs that only have a small percentage of the routing table entries cause suddenly 6% of all update messages. So you can kill the internet by flooding these update messages. So that's basically also a part of the message that yes, BGP has some issues with stability, that even very few prefixes can contribute to the majority of update traffic, which make the network unstable. So stability is an issue when you attack it, but also simple security, the peering. I mentioned that the peering is done via TCP connections. They can be encrypted, but what happens if the advertised data is incorrect? If you simply, well, say, oh yeah, this is the path to a certain prefix, which is not true. You can simply say that, yeah, I've got the perfect short path to whatever, YouTube. Okay, then everyone thinks, oh, this is the perfect AS for reaching YouTube. And all the traffic towards YouTube then goes via your AS. And this already happened. So the problem is that BGP, like many other protocols in the internet, is based on trust between the peering partners. And the original version even doesn't allow any verification of the routing data, and I will come back to this later. Okay. So that's just an example for, well, this. In the standard, it says the value should not be changed. The origin of a, well, it's one of the attributes of the path. And if you create routing information, you're the origin, You generate this attribute, and this should not be changed by anything else. Okay, but what happens if you change it? If you change it, well, somehow you're lying, but there's no one stopping you from lying. So you see that the standard itself, without any additional mechanisms, has no means to prevent you from announcing wrong paths or announcing a path on behalf of someone else. Okay, so just some basic questions. Scalability is the main issue. How do you handle scalability when it comes to routing to the real protocols? Okay, when we look to the standard link state and distance vector routing protocols, what is missing when we want to go to this global planet-wide routing between different domains, and how does BGP now handle these issues? And what was this again with this vantage point, and why do those routes depend on the vantage point? So even if I'm in the same AS, I have different routes to the same prefix. Why can this happen? And in this context, can you then create a total overview of the connectivity from your vantage point? Do you then see the whole internet, what happens there, all the connectivity between all the different autonomous systems? Or what is the problem here?